Hey everyone, today we're going to talk about proof of work. Now, proof of work is part of the consensus algorithm that was introduced with Bitcoin. Now, proof of work is a little bit controversial in the permission blockchain community because they seem to really want to replace it. But the thing about proof of work is that proof of work actually works. So it's something that you should know and understand, at least so that when you're having the discussion about consensus algorithms and you're talking about mining and permission blockchains versus public blockchains, you kind of got an idea where this whole idea of proof of work, or this concept of proof of work, comes from. So when we talk about hash algorithms, which I do talk about in another video, the hash algorithm that's at the center of all this is a hash algorithm called SHA-256. Now, SHA-1 was introduced by the NSA in 1995, and SHA stands for Secure Hash Algorithm. So what you're basically doing with SHA-256, which is the 256 version of SHA-1, what you're basically doing with SHA-256 is you're taking data of any size and you're folding it over and you're compressing it and you're boiling it down to 256 bits. Now, this 256 bits is actually a 64 character hexadecimal. So when you see the final output, it's not in zeros and ones, it's in zeros through Fs. So you get a 64 character length hexadecimal output from the SHA-256. So the important thing about this is that it's pseudo-random, which means you can't guess what it's going to be. There's an effect that's part of cryptographic hashing called the avalanche effect, which means that even the tiniest change in the data makes the largest possible change in the output of the hash. So we've got something that's pseudo-random, which means we can't guess it, but it's also deterministic, which means if I put the letters A, B, C in, I'm going to get the same hash every time. If I put the same data in, I will always get the same output. Now, hashing is not like encryption. It's a one-way function. So with encryption, you encrypt something, you scramble it all up with the idea of you're going to turn it back to its original form. Hashing doesn't work that way. Hashing loses data. Now, it creates this pseudo-random output that's deterministic, but it isn't something where you can take the fingerprint of the data and get back to the original data. Now, another thing about SHA-256 is it's fairly fast, and that's what we're using as part of this proof of work algorithm. Now, blockchain is like a recipe made up of a bunch of technologies from the 1970s. And one of the technologies that's actually a little bit later, which is from 1997, is called Hashcash. And that was developed by a guy by the name of Adam Back. And the idea behind this was to stop email scam and posting to bulletin board spam. What it requires is that you solve a little bit of a puzzle before you send an email. So what you would do is you would want to send an email off of a server, and it would make you solve a puzzle that takes, let's say, a half a second. Now, half a second is not a big deal for solving a puzzle if you want to send one email. And so if you're a legitimate email sender, it taking an extra half a second to send your email is really no big deal. But if you're a spammer and you want to send 1 million emails, well, that extra half a second is, killer to you. You can't do it because now you're going to spend all this time solving this equation to send an email and send your 1 million emails. So it was a way to prevent spam. Now, how it works is it requires a certain amount of CPU by using a SHA-256 function. And so what you would do is you would take the email message and you would run a SHA-256 on it. Then you would require it to have a certain number of leading zeros. And if it didn't have a number of leading zeros, you would add a thing called a nonce to it, which is just another piece of information, and then you would try it again. And if that didn't start with a 0, you would change the nonce, you'd make a different nonce, and then you'd try it again, and if it still didn't lead with a 0, you would keep doing that. And you would do that over and over and over again until you got a certain number of zeros to meet your requirement that the the message plus the nonce starts with a certain number of leading zeros. So the number of leading zeros is called the difficulty. So because it's 64 hexadecimal characters, the chance of the first number being a 0 is 1 out of 16. It's no big deal. A computer is going to bang 1 out of 16 and no problem. Well, to do 2, it's 1 out of 256. To do 3, it's 1 out of 4096. To do 4, it's 65536. Now it's getting interesting. Well, now if you get to where Bitcoin is today, it's 18 zeros. So you have to determine a block on Bitcoin, you have to run a hash algorithm that takes the data from the block, adds a number to it, and the hash that comes out of it has to start with 18 zeros. So the number I have up on the screen, I don't even know how big a number that is. It's 16 digits. It's e to the 16th. So that is bigger than the number of grains of sand on the earth. It's an incredible, incredible number. So even with extremely fast ASIC chips, which are these advanced chips for just solving the SHA-256, it takes hundreds of thousands of miners 20 minutes to find a number that starts with 18 zeros. So what that's doing is it's proving that a certain amount of CPU difficulty went into creating that block. Now, you might ask, well, why is that? That seems ridiculous. Why would you waste so much energy, waste so much CPU time to create a hash, just an arbitrary hash that begins in 18 zeros? Well, what that does is it actually protects the blockchain, because you know that that much CPU needs to be expended to create a block. Well, what that'll do is that will prevent somebody from going back and changing a prior block. Now remember, with the blockchain, every block is dependent on the block before it, which is dependent on the block before it, which is dependent on the block before it. So even if you wanted to go back just, let's say, 5 blocks, you would have to do as much proof of work to replace those 5 blocks as these 100,000 miners are currently executing. So the longer the blockchain gets, the less likely it is for somebody to be able to go back and change data. And so that's why you can depend on the blocks of the blockchain being authentic, because it would take so much work to create them. Now, proof of work is one of many consensus algorithms. Now, it is actually the one that works. Now, there have been changes in a lot of different coins where they don't use SHA-256 anymore, because once it became profitable to do so, there was hardware solutions. The ASIC chip is 20,000 times faster than a GPU, which is, I think, 2,000 times faster than a CPU. So you can use a different hashing algorithm so that you can require more work be done, and so that it isn't as done with dedicated equipment. But by doing this, you're protecting the blockchain. Now, other consensus algorithms there's delegated Byzantine generals. There's practical Byzantine generals. There's these other permission blockchain technologies that are used to replace proof of work. But proof of work is really the starting point. It's really the thing that, there's 2,500 coins out there, 2,500 blockchains out there that are using proof of work. Now, they're not all using 18-digit numbers that start with zeros, and in a lot of cases the proof of work doesn't even depend on it starting with a 0. But proof of work is really that foundational technology that is part of the blockchain that is used to protect the blockchain.